Hi everyone, welcome to current mesh analysis. This is the second video in a two-part series on current mesh analysis. The first video, if you haven't seen it, was on the understanding behind this process and its intended procedure. This video here is refining our procedure to make it quicker and easier for you guys to take into exams. So just as we did in the first video, we need to define a reference node first. Now a reference node is the point of lowest potential in our circuit, or is essentially ground. Again, we have the same three-step procedure. Our first step is to define our mesh currents. Our second step is to write KVL loop equations. And our third step is to solve these equations. Mesh loops are the windows we see inside of our circuit, or basically loops that we can draw around that connect to each other. So we can see we have one here, a second in the middle, and a third out here. So those are our mesh loops. Now step one is to define our mesh currents. And what we do is essentially assume that we have a current traveling around the loop in this direction. And we do that for each of our meshes. We then label them something different. So IX, IY, and IZ is what I'm going to call mine. So that is our first step done, defining the mesh currents. Our second step is to write our KVL loop equations. If you need a recap, KVL, or Kirchhoff's voltage law, is the sum of voltage rises equals the sum of voltage drops within our loop. The first part of the procedure is the same. We start at our reference node and we work along the path that the current IX is taking. So we start at our reference node and work upwards. We then reach the negative terminal of a battery source and move to the positive terminal of a battery source, which is a voltage rise of V volts. So we write that on our voltage rise side of the equation. This is for mesh X as well. So this in here is mesh X. So again, we have a voltage rise of V volts in mesh X. If we then continue along the path that the current would take, we reach a resistor. And this is where we come to a difference in our two procedures. In this second method, I want you guys to forget about the positive and negative terminals of resistors and always take resistors to be voltage drops. So in this first resistor, we have a voltage drop of IX times R1, as we're still saying IX is traveling around this loop. As I trace around the path further, I then get to R2, where we have that classic clash of currents between IX and IY. So for a recap, we have resistor R2 running down like this, IX traveling in this direction, and IY traveling back up in this direction. Now in this second method, we always take the mesh we're looking at and subtract the mesh we're not looking at. So I'm in mesh X. So what I do to write the voltage drop over R2 is R2 times the mesh I'm looking at, IX, minus the mesh I'm not looking at, IY. And as we travel past R2, we get back to where we started without encountering any more components. So that is our mesh X equation done. Our next step is to go into mesh Y, which is this mesh here with current IY. Mesh Y. Again, we start at our reference node and work around along the path of the current, and we first reach R2. So, like I said before, in this second method, resistors are always voltage drops, which means if we take a quick look ahead in this loop, we don't have any battery sources. We only have resistors, which means we're only going to have voltage drops. So when writing our KVL equation, our voltage rise side of the equation is going to be 0. So we have 0 equals our voltage drop over R2 that we encountered first. So that's going to be the resistance R2. And remember our trick here, that it's always the current in the mesh we're looking at minus the current in the other mesh if we have a clash of two currents. So that makes this voltage drop over R2 in mesh Y, R2 times IY minus IX. We then keep on moving around the loop and we reach R3, another voltage drop, which is going to be R3IY Continuing around the loop, we come to R4 where we have another clash of currents. Our voltage drop here is going to be R4 times the current in the mesh I'm looking at, IY, minus the other current that is interfering, so minus IZ. And there we have our mesh Y KVL equation. Our third mesh is mesh Z. And again, this is where we have the current source, which defines what IZ is. So our current source is moving anti-clockwise around this loop with a magnitude of I. As we define IZ to be moving in the clockwise direction, what we get from this loop is IZ equals negative I, as it's moving in the opposite direction to the current source. So again, once we're at this point, we have our three equations for our three unknowns, and it's just a matter of simultaneously solving the system for Ix, Iy, and Iz. Just as a quick note, you'll notice if you look back to part 1 that our three mesh equations are going to be the same. Otherwise, they wouldn't be equivalent methods. The only difference between the two methods is in our mesh Y equation, where our voltage drop over resistor 2 was on the left-hand side of the equation as a voltage rise. So it was over there. But we'll notice that it was on the left-hand side of the equation, but it had Ix minus Iy. So you can see that these are the equivalent, because if I wanted to take this term to the other side, well, I would subtract it away. So we would have minus R2 Iy minus Ix, which is the same as R2 times Ix minus Iy. So it's only a very simple difference in algebra, but doing this second method is a much easier process to get your head around. So of course you can choose either of the two methods we've looked at here. This method, however, you don't have to worry about the plus minus terminals on the resistors or the direction the current's going. All you do is kind of compute the mesh analysis process, which is why a lot of people find it a lot easier to follow. I would recommend just choosing a method and practicing that one method. So I hope you guys enjoyed, and if you have any questions, please feel free to let me know.